All right. All right, we're going to go through some definitions first and go through the gas laws, and then we will get into the basic refrigeration cycle, and we'll see how that all relates. I know modules 1 and 2 are tough, a lot of formulas, a lot of talk about how many BTUs does it take a 10-pound block of ice at minus 10 degrees and make it into 250 degree steam, but that's all for a purpose. We'll kind of get into that in just a bit. Okay, the first definition, heat. Now, when you think of heat as a human being, that is like your stove and it's hot and you get burnt. But truly, heat is just a form of energy and it's molecules in motion. So even with an ice cube that's at 32 degrees, there are molecules in that ice that are moving and there's still heat there. Um, it isn't until you get down to minus 460 degrees and all molecular motion stops. And that's never been reached yet. You can get down pretty close to that. But so I want you to start thinking of heat as molecules in motion, not so much as something that is hot to your touch. And heat always flows from a substance that has more heat or more molecules and motions to one with less heat. This will give you a quick example right here. For example, this block of ice at 32 degrees does have molecules in motion, but they're pretty much bonded together and they're not moving very much. They're just sitting here um, while they are moving, they are not bouncing into each other too much. They're more or less bound together, and that's why that gives ice its solid form. And as we start to add heat to the ice and it begins to melt, the molecules begin to move a little bit faster. So not only are they bound together, they start to cut loose their binds with each other and turn into a liquid, and they start to exert some force in the downwards and outwards direction, like in this container. Then as we add more heat and we turn this water and liquid into vapor, those molecules are bouncing around really fast and it exerts pressure in all directions. And that's the one thing you need to remember when we're talking about pressure. That's where you get pressure. That this example here that shows that blows the cork off the bottom. You get so much energy and pressure in here that in the form of heat. Okay, heat flow. When I talked about heat earlier as molecules in motion, so this makes sense to us. If we have a 100-degree Fahrenheit block of lead here and set it next to a 75-degree Fahrenheit block of lead, of course, we recognize that the heat will flow from the substance with more heat or molecules in motion to one with less. But now we don't usually think of minus 200-degree Fahrenheit and minus 350-degree Fahrenheit as having heat, but it still does. It has molecules in motion, although not as much as these blocks up here. There is heat energy contained in this block of lead, and the molecular motion or heat energy will in fact flow from a substance that is minus 200 degrees to minus 350 degrees Fahrenheit. And that's why I want you to think about heat again as molecules of motion, not something that is hot or cold to our touch. All right, there's in air conditioning, we have two forms of types of heat that we like to talk about. One is sensible heat, and that is where if you add heat or molecules or heat energy in molecules in motion as to a substance, it changes the temperature that you can measure with a thermometer. And then we have latent heat, and that latent means hidden, and that's heat that cannot be measured by a thermometer. And what it does is at a certain point, and if we use water in the example in the textbook, when you start with a 75-degree pan of water and put it on the 500-degree stove, it starts to increase the temperature. And if you have a thermometer in there, it's going to show that temperature increase. That's the sensible heat. At a certain point, if you're at sea level, it's 212 degrees, the water begins to boil, and that's changing of state from a liquid to vapor. And it remains steady at 212 degrees and will not, that water does not increase temperature because all of that heat energy that's being absorbed is changing the state of the water from liquid to vapor. That's called latent heat because even though you're adding heat, you can't measure it with your thermometer. Okay, saturation. And we'll talk about water first, then we're going to talk about refrigerants because they're very similar in their properties. The saturation is when a substance is in the form of both liquid and vapor, and if heat is added, it'll begin to change state into vapor. And if heat is removed, it will change state back into liquid. So the definition of saturation is when a substance is in the form of both liquid and vapor. When we add heat, it changes state, begins to change state into vapor. And when we remove heat, it will begin to change state back into liquid. And I just want to let everyone know, if you do have audio problems, please call in on the number up at top. I just got a message from one of our viewers here. Okay, changing state. And this is very important. When we are changing state of a liquid to a vapor, it takes a tremendous amount of heat energy, and which are molecules in motion, to change that state from liquid to vapor. And when that condenses back down from vapor to liquid, all the energy, the heat energy that's been absorbed, is released. So when you boil your water, all that heat energy, when it hits your cool window and turns back into water, releases all of that heat back into the atmosphere. Okay, and from now on, I want us to not to think about boiling anymore, because that's just like heat for us. Boiling, we equate to water and it's hot. We want to think about changing state rather than boiling, because it gets confusing with refrigerant. Again, it makes sense when you have a beaker of water here and you're adding heat to it and it's boiling and you put your finger in there and you get burned. But when we talk about refrigerants, they boil at much lower temperatures. So we're gonna erase boiling from our vocabulary, and changing state is what we're going to talk about from here on out. All right, so here is the diagram from our textbook, and it starts out at the bottom of the graph with 0 degree ice. We're not going to worry much about this 0 degree ice until we hit 32 degree water at this point right here. Let's talk about this water. We have that water on the stove like we talked about earlier, and as it is heated up on the stove, the temperature begins to rise. At this point, we're at 100 degrees over here. Now, as that heat that is being added raises the temperature, that is the sensible heat. Remember, sensible heat is heat that can be measured with a thermometer. At 212 degrees, our water is at saturation. It's at its saturation point. It is absorbed as much sensible heat as it can absorb, and any heat that is added from this point on changes the state of the water from liquid to vapor. And it doesn't matter how much heat we put on there, as long as we have both liquid and vapor together, it will absorb a tremendous amount of heat to change the state from liquid to vapor. At a certain point, when all of the liquid has been changed to vapor, it will again start to pick up sensible heat here, and it raises the temperature of the steam. Now, I want you to take a look at this. If we take 32-degree water and we go back down here, it is 160 BTUs to get it to that point. And then we raise the temperature to 212 degrees. It only takes 180 BTUs of heat to do that. That's not a lot of energy in the form of molecules in motion. So raising the temperature of something really doesn't absorb or release a lot of heat. But when we hit this point right here where it's at its saturation point, and we take that pan of water and we turn it from liquid into vapor, it takes 970 BTU of latent heat to do that. And this is with 1 pound of water. So this is where the refrigeration process happens. Not with water, but with refrigerant. So I want you to remember that changing of state requires a tremendous amount of heat in the form of molecules in motion. And if we go backwards down this chart, and we hit the saturation point where it is almost all steam and just starting to turn into liquid, from vapor to liquid, all of the heat that we gained as we travel back down from vapor to liquid, all that 970 BTUs is released from the water until it hits 211 degrees, and then it's going to start losing its sensible heat. Again, this is where the refrigeration process takes place. All right, superheat. Once that liquid, and in this case water, but refrigerant as well, once that liquid has changed state completely into vapor, adding any more heat will increase the temperature. Now, that's where we talked about right here. We have changed the liquid vapor combination into 100% vapor. Any heat that is added, this is our superheat. Heat that is added is called superheat, and this is where this happens. So that is this part of the chart right here. So when you think about superheat, it is heat that is added above the saturation point after it turns into 100% vapor, whether it be water or refrigerant. So if you measure the temperature, of your refrigerant or water, and you subtract the saturation temperature from it, what is remaining is the superheat, and this is when it's in the vapor form. Now, this has a lot to do with refrigeration troubleshooting, which we'll get into in another webinar, but superheat and subcooling are important. So subcooling. Okay, so once our vapors change completely back into liquid, and we're 100% liquid, removing heat will decrease the temperature. So we're removing sensible heat. So if you take your saturation temperature and then you measure the temperature of the liquid, the difference is subcooling. Now, on our chart, that's what happens right down here. So here we're at saturation point. We're dumping all of the latent heat. At this point, from here downwards is our subcooling. So we'll get into this again in more detail, but actually the entire refrigeration cycle happens between subcooled liquid through the saturation point up to superheated vapor, and then back down again down to this chart. When we get into the refrigeration cycle, we will explore this chart a little bit further. Okay, gas laws. I know they had Boyle's law, Dalton's law, the law of combined gas. What you really need to know is if you compress a gas and reduce its volume, both the temperature and pressure will increase. So if you have a piston and you put air in that piston and you compress that piston, you think about it, heat and pressure are molecules in motion. So if you reduce the amount of space those molecules have to bounce around, that heat is increased, and so is the temperature. And conversely, if you expand that gas and pull that piston back down, both the temperature and the pressure will decrease because those molecules that are in motion don't bounce as fast and against each other to create that heat and pressure. So that's the one thing you need to remember with the gas law. If you increase pressure, you increase temperature. If you increase temperature, you increase pressure as well. And the same thing, if you decrease the pressure, you decrease the temperature. They happen together. Okay, and here's an example of that. So here's our piston, and we fill this piston with air, and it's at atmospheric pressure, which is 14.7 psi, and we reduce this piston by half the size. We compress this gas, and we reduce the volume in half. It doubles the pressure. It's also going to increase the heat because these molecules are bouncing around in here at a whatever rate they are. But if we decrease the area and the volume of where these molecules bounce around, they bounce around faster. And when they bounce around faster, remember, heat is our molecules in motion. The more motion, the more heat that's generated. Okay, and this is just an illustration here of a bottle of liquid that's at its saturation point and it's refrigerant. At 75 degrees, it's 132 psi. And if we reduce the temperature, it reduces the pressure as well. And if we have this jug over here and we vent off some of this pressure, and decrease the pressure, it's also going to decrease the temperature. So remember, pressure increase, temperature increase, pressure decrease, temperature decrease. Make sense? All right. Now, we're still again talking about water. The changing of state of water at atmospheric pressure happens at 212 degrees Fahrenheit. And we can see that right here. This is a pressure temperature chart for water. And the way, when we're looking at any type of pressure temperature chart, this is talking about saturation, temperatures and pressures. That's when we are both liquid and vapor. And if we add any heat, it's going to change state from liquid to vapor. And if we remove heat, it's going to change state from vapor to liquid. Once we're 100% liquid or 100% vapor, this chart right here has no bearing whatsoever on what's going on. So this is a pressure temperature chart, or PT chart, for water. And we have these charts for refrigerant as well. But let's look at this. This is atmospheric pressure down here at the bottom, 14.7 psi. And at atmospheric pressure, water will change state at 212 degrees. Now, let's say we reduce that atmospheric pressure and we put the water into somewhat of a vacuum. We can change the state of that water at 70 degrees Fahrenheit. And the same thing happens if you increase the pressure, and it increases the temperature that the water changes state. And we'll get into this again when we get into the refrigeration cycle. This will start to make some more sense. So at 15 psi in a pressure cooker, water doesn't change state until it hits the 250 degree Fahrenheit range, and that's when it hits saturation, where it's both liquid and vapor are present. And if we add heat, it's going to change state from liquid to vapor. And if we remove heat, it's going to change state from vapor to liquid. Okay, and this is just an example. If we have a bell jar and we have a vacuum pump and back it out, we can make water change state at 70 degrees Fahrenheit. All right, so let's get into the basic refrigeration cycle step by step. We'll talk about saturation, superheat, subcooling, changing of state, and the energy that's required to do this, the refrigeration process as we go along here. All right, so let me clarify some things here to make a little bit more sense. This signifies the wall in your home. On this side of the wall is the indoor unit. This is the blower where you change your filter. Here's our fan. Here's our cooling coil or evaporator coil right here. These are the lines that connect, the copper lines that connect the indoor unit. Now yours may be in a closet, in an attic or garage crawl space, wherever it may be. This part is the indoor unit. Here are copper lines. They pass through the wall. They go out to the outdoor unit, which is the condenser. And this is what sits outside your home. Here's the condenser fan. Here's the condenser coil. Everything else has been removed from this diagram to help us get a better idea of the refrigeration cycle. Now, I know our textbook starts the refrigeration cycle at the compressor. I like to start it here at the metering device. And right at the beginning of the metering device, we're going to start. So we will start, and we'll get back to this point, and we'll end up right here. We are going to start with 100% liquid refrigerant entering the metering device. And for the sake of this webinar, we are going to just take a look, think about our metering device as a restriction in our line right here. And what it does is it will, whatever type of metering device it may be, it will reduce the pressure as the refrigerant moves through the metering device. Now, our gas laws tell us when we reduce pressure, we also reduce temperature. So at this point in the refrigeration process, after the liquid refrigerant has passed through the metering device, the refrigerant itself is 25% vapor and 75% liquid. And remember, that puts it right from liquid directly into its saturation point, because saturation is when we have both liquid and vapor present. So we now have saturated refrigerant at our indoor coil. And we have our indoor fan that is blowing 75-degree room air across our evaporator coil with our saturated refrigerant in there. And remember, when refrigerant or anything else is at its saturation point, if you add any kind of heat, it's going to change the state of the refrigerant. So it's going to start, it's already 75% liquid and 25% vapor, and it is going to continue to change state as it passes through the evaporator coil. And it's changing state from liquid to vapor. And remember that when we are changing state, that requires a tremendous amount of heat energy. So all of the indoor 75-degree air that's passing across this coil, the heat energy in the form of molecules in motion are being removed from the air. So as we remove the heat, we're able to now blow out 55-degree Fahrenheit room air and begin to cool the home. So we really don't cool the house. We remove the heat from the air, which makes it feel cooler. Now let's take a look at something here. So we're at 75% liquid, 25% vapor as we exit the metering device. And we are at 69 psig, which equates to 40 degrees Fahrenheit. Now this is the PT chart that we have in our book. And let's just verify that. Now remember, we talked about the PT chart. This only has it only relates to our refrigerant when it's at the saturation point. So that's when we're at that saturation point right now at the coil. Now in this example, we're using R22 refrigerant, which happens to be this column right here. And if we go back, we're at 69 psig. So let's take a look. Let's go down this chart. And this is our pressure column for R22. And at 69 psig, which is right about here, if we read it over to our temperature column, you can see that when we have saturated refrigerant at, for the sake of argument, 69 psig, it is 40 degrees. And you can see here, our gauge reads 69 psig, and we have our thermometer on. We can't really measure this in the coil, but for the sake of our class, we do. If you could measure that coil, we would read 40 degrees. And as this saturated refrigerant passes through the evaporator coil, it is starting to change state more and more and more, and we're going from changing state from liquid to vapor, picking up more heat in the form of latent heat. Again, that's changing of state. And at this point, we're at about 50-50, 50% vapor, 50% liquid, and we are still at 69 psig and still at 40 degrees Fahrenheit because we're still at that saturation point. Remember, any heat that's picked up is not measurable when we're at the saturation point. It changes the state of the refrigerant. So it's changing state from liquid to vapor as we move through the evaporator coil, and it's sucking the heat out of the indoor air. Now, at a certain point where the engineers designed this coil, we are now going to change this refrigerant is now no longer going to be at its saturation point. Although it's still at 69 psig, we are now at the 100% vapor point. And from here on, we are no longer picking up sensible heat. We're no longer picking up latent heat, we're picking up sensible heat. And if we put our thermometer on the line after we have changed the state of that refrigerant completely from liquid to vapor, we can now start to measure the sensible heat of the refrigerant. Remember, when we talked about our sensible heat, let's take a look at that in this chart here. So here's the point where the refrigerant enters the evaporator coil. It's at 75% liquid, 25% vapor, and as it travels through the evaporator coil, it's picking up all of the heat and changing state. And that's where all the heat energy is absorbed into the refrigeration system. And at this point in our evaporator coil that we just looked at, we're now at 100% vapor, and any heat that's gained is sensible heat, and that is our superheating point right here. There is really no cooling that happens with the superheat. We have superheat to make sure that we have 100% vapor going back to the compressor. So we're going to go through this quickly again. So we have solid column of subcooled refrigerant hits our metering device. Metering device drops the pressure, which drops the temperature. It changes us into the saturation state, where we have 75% liquid and 25% vapor. That refrigerant is flowing through the evaporator coil, and the heat energy from the indoor room, again, the 75 degrees in the room, we're at 40 degrees Fahrenheit here. Heat travels from a substance with more heat to a substance with less heat, and those molecules in motion and all that heat energy is used to change the state from liquid to vapor in the evaporator. At a certain point designed by the engineers, we hit 100% vapor, and any heat that's gained is in the form of sensible heat, which is our superheat, and that makes sure that we have 100% vapor going back to the outdoor unit to the compressor, because we all know you can't compress liquid. All right, so we hit the compressor with 100% vapor that has 20 degrees of superheat added to it. It's 100% vapor. Now remember our gas laws. So when this compressor compresses the refrigerant, it increases the pressure, which increases the temperature. Now we have 20 degrees of superheat in this vapor, and after it comes out of the compressor, it still contains that 20 degrees of superheat. And as that refrigerant travels out of the compressor, it is beginning to cool down, and it's de-superheating, and it's just letting off the sensible heat as it enters into the condenser coil. So we're at 278 psig, and at a certain point in the condenser coil, we are going to hit the saturation point of this refrigerant. And if we take a look right here, 278 psig, here's our R22 column, here's our temperature column, this is the saturation point, 278 psig for R22 means it's at 125 degree temperature. Now, we know that heat travels from a substance with more heat, more molecules in motion, to one with less molecules in motion. So our outdoor air is 95 degrees Fahrenheit. Our saturated refrigerant is at 125 degrees Fahrenheit. So that heat is traveling and leaving the 125 degree condenser and is being dumped into the 95 degree air. So from this point on, we are now condensing back from vapor, 100% vapor, and then we start to travel through the evaporator coil, and we are condensing back down into liquid. So all the heat that we picked up over here has been carried outside, and we're dumping it outside. Remember that all that heat energy in this evaporator coil is now being released outside. So now we're condensing back from vapor to liquid, and as it travels through the evaporate or the condensing coil, all of that tremendous amount of heat energy is being released. And again, if we have a thermometer at any point in the condensing coil, as long as we're at the saturation point, it's 125 degree Fahrenheit. Now, I just saw a question pop up there. Let me take a look at that here, and I'll answer that question. Okay, Andrew, I'll get back with you on that question. Okay, so we are at the saturation point through the condensing coil. We're dumping the heat to the outside air, and at a certain point, we are now back to 100% liquid. Now, now the heat that is being released from this liquid is in the form of subcooled liquid. And let's take a look at that. Take a look at our chart here real quick. All right, so let's take a look at what we just talked about. So here's our sensible heat. Remember, this is our superheated vapor point right here. It enters the condensing coil, and we are changing from 100% vapor back down to 100% liquid. At the point where it's 100% liquid, we start to pick up sensible heat. So this is our subcooling point. So if we took our refrigeration cycle and we started right here at the, well, we're going to start right here. We'll start right here with subcooled liquid that hits our metering device. It goes immediately from subcooled liquid to its saturation point, travels through the evaporator, boils off the refrigerant, which is changing state. It takes tons of heat to do that, absorbs all that heat till it's 100% vapor, and then it goes into the superheating part where it's picking up sensible heat. At that point, it hits the compressor, it gets compressed, and the first part of the condensing coil desuperheats, removes the heat. We hit the saturation point. It comes back down as it condenses back down from the saturation point into 100% liquid, goes through the evaporator, or the condenser, excuse me, and it becomes subcooled liquid again. Then it hits the metering device, goes back through the evaporator coil, and that is our refrigeration cycle. So what we do is we take, actually in refrigeration, is we take heat from a place where it's not needed, which is your home, and we take it and release it to a place where it really doesn't matter, which is outside. And it's all done through the refrigeration process. So let's go through this one more time, then we'll have about 10 or 15 minutes for questions and to wrap this up. All right, so we're going to start. We hit our metering device with a solid column of subcooled refrigerant. The metering device immediately drops the refrigerant from subcooled into the saturation point where it's 25% vapor and 75% liquid. Travels through the evaporator coil where the indoor room air is blown across the evaporator coil, and the heat is from the indoor room air is transferred from the room air and is used to change the state of that refrigerant, and that requires tons and tons of heat energy to do that. So we are changing state all the way through the evaporator coil till we hit the certain point where we have, is designed by the engineers, all of the refrigerant is boiled off, and we are now 100% vapor, and any heat that is picked up doesn't really cool anything, but it does ensure that we have 100% vapor heading back to the compressor. So we have superheated vapor coming back to the compressor. The compressor uses the compression cycle to increase the pressure, which in turn increases the temperature, and we have superheated vapor leaving the compressor. As it travels through the first part of the evaporator coil, it is shedding all of the superheat. That's called desuperheating until we hit the saturation point again of the refrigerant, and we're changing state back from liquid to vapor. As it travels through the evaporator coil, all of that heat that is picked up inside the house is now released outside as it changes state. At a certain point in the condensing coil, we have now changed all of the refrigerant back into liquid, and we have subcooled liquid. We have the subcooling process, which makes sure that we have 100% liquid coming back to the evaporator coil. Now that is our refrigeration process. That's the basic refrigeration process. Now, if you're in one of my students in the HVAC class, we're going to go through this again using a TXV. We'll talk about overcharging and undercharged systems and how that affects the refrigeration cycle and system performance as well. So I saw we had a couple of questions, so let's see if we have any. And Andrew, if you just want to hang on there, let me know, and then I'll chat with you in just a bit. Okay. I just had a question about how can I get involved in the class. I do have, if you go to HVACtrainingsolutions.net, I do have an HVAC technician class, commercial refrigeration for HVAC technician classes, and NATE test prep courses. And if you're interested in doing that, you can reach me at hvactrainingsolutions@gmail.com. Thanks for that question. That wasn't a plug. That was really a question. Question: is it applicable to Canadians as well? This HVAC class that I have gives you the basic knowledge and understanding of the refrigeration process, as well as electronics and the reading schematic diagrams, safety, tubing and piping, and so forth. This prepares you to take an HVAC exam should your state or country require that, and gives you the basic knowledge needed to get an entry-level position as an HVAC technician. Okay, last chance for questions. I'd like to thank everyone for coming. If you go to hvactrainingsolutions.net, we do have our online training calendar, and you can check out our training there. And Joe, I'll ask if you want to stay late and have any questions answered, please feel free to do so. The rest of you, thank you very, very much.